Here we want to look at some different values for the sine curve. When we generate a sine voltage, we know that the instantaneous value is lowercase letter u, and it is the maximum value multiplied by sine for the angle that the wire or conductor is turned or rotation of generator. The maximum value, it can be both positive and negative, since when we got the sine curve, we have the maximum value here, and also we have the maximum value here. Here we got a negative value, here we have a positive value, but the value is the same. So this is just a number for the maximum value, and it is not necessarily positive or negative. Then we have the peak-to-peak value. That is the value from minimum to maximum. And if it is symmetrical, it is 2 times the maximum value. Because when we look at the sine curve, here we got the minimum, here we got the maximum, and here we got the maximum value and the maximum value. So peak-to-peak value from the bottom to the top, it must be 2 times the maximum value. Then we got the average value, and that's the average of the voltage, and we measure only over a half period. It is because if we see the sine curve, if we take the average of one complete period, we can see this area is the same as this area. So actually the average value, if we look at a complete circle or period, the average value is 0. So we just look at here from 0 degree to 180 degree, and then get the average value for this voltage. And the average voltage is the maximum voltage multiplied by 2 divided by pi, and we'll try to find out if this formula is correct. Then we got the effective value, and that is the voltage that gives the same power at AC and DC. It means that if we connect a resistor to a DC voltage, we can say 230 volt. We have that in the supply system in Denmark. And if we connect the same resistor to 230 volt AC, and 230 volt is an effective value, then the power that is consumed in the resistor is the same. It doesn't matter if we connect it to DC or AC. So we have the formula out here that the effective value is the maximum value divided by the square root of 2. And we also try to find out if this formula is correct. Finally, we got the form factor. This Greek letter KSI, and that is the effective value divided by the average value. And over here we just put in a formula for effective and average value, and we divide 2 fractions by multiplying the reverse. So we got this formula, and we can delete U maximum, and we got pi divided by square root of 2 times 2, and that is the same as pi divided by square root of 8, and it is 1.11. So the form factor, that is the effective value divided by the average value, and for a sine curve it is 1.11. If we have another curve form, it can't be another number. We'll first see the average value and try to find out. And first we'll have to find out the maximum value, because we know that in a Danish system we got that the voltage is 230 volts effective, and if we multiply by square root of 2 we got the maximum value. So 230 and multiply by square root of 2. Then we have a maximum voltage of 325 voltage. So actually in a Danish supply system we have the peak-to-peak value, that is 2 times the maximum value. So we have 650 voltage from minimum to maximum in a Danish supply system. When you look at the sine curve, we can see up here that is not 325 but 3.25. I just have divided by 100, otherwise we get very high numbers. So the formula for this sine curve is 3.25 multiplied by sine for x. We put on a d because we want to have it in degree. If we don't put on lowercase letter d, we work in radian, but we want to work in degree, so we have the angle in degree. So we can see the voltage here, 0 degree, 90 degree, we got maximum, 180 degree, again get 0, and 360 degree, we get 0, and 270 degree, we have maximum, it is just negative. And we want to find out the average, so we want to find out the area underneath the sine curve for 1/2 period. And if we then divide by the length of 180, we got the average value for this voltage. So we calculate the area or get help from Graphmatica, and here we can see we want to integrate this formula from the angle of 0 to 180 degree and calculate. Then we got an area of 372.4159. Take a calculator and put in this number, 372.4159. That was the area, and then we have to divide by 180. So we have an average value of 206.9 volts, or 2.068 if we just take the numbers here on the y-axis. And now we want to find out if this number is the same as the formula described in the document. We have that the average voltage is the maximum voltage multiplied by 2 divided by pi, the formula said. The maximum voltage was 3.25. We multiply by 2 and divide by pi. And yes, we have the same value or nearby. It's very close to. And I think small error is because that we in Graphmatica we don't have a total number for the area. So it seems to be correct that the formula for the average value is maximum times 2 divided by pi. Then we want to look at the effective value. That was if we connect a resistor to the circuit, the power should be the same if we connect it to DC or AC. So the power for DC must be the same as the power for AC. If we set that the resistor that we connect is 1 ohm, it will be easier for us to find out. Because the power for DC is square of the voltage divided by the resistance. And if the resistance is 1, then the power for DC is just the voltage squared. The power for AC is also the voltage squared divided by the resistance. I just have put in a lowercase letter u because to get the instantaneous value, because if you see at the sine curve, the power will change all the time when we connect it to AC voltage. So actually here, when the voltage is 0, the power at the moment, instantaneous value for the power is 0. And the power, when the voltage is maximum, the power must also be maximum. But we want to take this formula and square. So we got value for the power. And we can see here, yes, the power is 0 when the voltage is 0, and it is maximum when the voltage is maximum. And if we go back, we said that the power for AC is the voltage squared divided by resistance, and resistance is also 1 here. So actually also here, the power for AC is instantaneous value for the voltage squared. And we have just calculated that in Graphmatica. So we want to find out the average value for the power, and actually this curve for the power is the sine curve, and we know that the average value for the sine curve is the middle. You can see when the sine curve is symmetrical. So the average value for this one should be the half of the maximum. We can see up here the maximum is 10.56, and the half, you just can try to use a calculator. 10.56, take the half is 5.28. So we think that the average value for the power should be 5.28. We can try to calculate it by using Graphmatica. So again, try to calculate the area for the other curve. And again from 0 to 180 degrees. And now we have squared area here. It is the total power of the area, 950.625. And we can take the calculator, 950.625, and divide by 180 degrees to get the average value. And we got 5.28. So the average value is 5.28. We go back to the formula, and we can see that again the average value for the power for AC is 5.28, and the voltage is the square root of the power. So the effective voltage must be the square root from the, is the middle, that's Danish words, AC average. So we got that the effective voltage is square root of the average power for AC. And we find out that the average power for AC was the maximum power divided by 2. And if we got a square root of a fraction, we can split it up and take a fraction and the square root of the AC max, power of AC max, divided by square root 2. And square root of AC power maximum, we can see Graphmatica that here we got the maximum of power, and we take the square root of that, we got the voltage. So we can say again that this is maximum voltage divided by square root of 2. So that's the formula, and now we can try to calculate and see if it's correct. We have here, that was the average of the power, and the power again, DC, that is the voltage square, and to get the voltage then we have to take the square root of the power. So we can take the square root of 5.28 and we get 2.298, and we remember that we have divided by 100 in the beginning of the voltage, so here actually we got 229.8 volts, and that is very nearby 230 volts. So it seems to be that the formula for the effective voltage seems to be correct, that it must be the maximum voltage divided by the square root of 2. So that was the relationship between maximum voltage, effective voltage, average voltage, and we talked about the form factor, peak-to-peak voltage, and we have tried to make it clear by using Graphmatica.